Hey everyone, welcome back to my channel, the Travlin Prof. In this video that we're releasing today, we are going to discuss our second part in the series about logical principles. And in this part, we are going to discuss the laws of logic. Part 1 was all about basic concepts in logic, including the definition of logic, which is reasoning conducted according to strict principles of validity. In other words, logic uses a strict form of sequential thinking to determine whether a statement is true or false. We also learned about statements, which are the most basic building blocks of logic. We said that a good logical statement must be, first, free of context. It cannot require someone to understand our personal experiences because no two people will arrive at the same conclusion based on this data. Instead, we understand that statements must be intentional declarations of fact that exclude unverifiable context. A good statement will, therefore, be verifiable by anyone who has access to the same information. And finally, when we arrive at a conclusion about a statement's validity, that conclusion must be either true or false. There is no middle ground in logical thinking. After defining logic and explaining what a statement is, we learned the basic principles of logical notation. So far in our study, we have learned 4 kinds of symbols. First, we represent a whole statement with a single capital letter. Second, we represent the conjunction word, which is and, with the ampersand. Third, we represent the disjunction word, or, with a caret. And fourth, we represent the denial of a statement with a dash preceding the statement letter. After we learned the symbols, we spent most of our time learning about their influence on a sentence's truth values. We already said that a statement must be true or false, so let's continue on. That is, the denial of a statement will result in the opposite truth value of the original. So if the original statement was false, then the denied statement will be true. And if we deny the denied statement, once again, we arrive at false because we've gone opposite 2 times. The third rule that we discussed is that when combined by a conjunction, a sentence is only true if all of its parts are true. Thus, the sentence, "It is raining and snowing," is only true if it is both raining and snowing. Then fourth, when combined by a disjunction, a sentence is true if even one of its parts is true. Let's use our example weather sentence yet again. We know that the sentence, "It is raining or snowing," is only false if neither rain nor snow is falling from the sky. If rain or snow, or even both, are falling, then the sentence will overall be true. Now that we have caught back up to speed on the last lesson, let's begin part 2 with the definition of logical equivalence. Logical equivalence is the principle that sentences are logically equivalent if they have the same truth values in all cases regarding joint truth and falsity of the sentence letters that appear in them. Now that's pretty complicated, so let's simplify it just a bit. Note that this definition is referring to sentences. Sentences can be composed of one or more statements, which we represent with capital letters per our rules for logical notation. That is what sentence letters in this definition is referring to. Next, joint truth and falsity means that the statements in the sentence must be joined together logically, with either a conjunction or a disjunction. There are some additional ways, which we will study later on, but for right now, that's all we need to worry about, conjunction and disjunctions. The same truth values refers to the practice of making truth tables like we did in part 1. So in order to demonstrate the definition of logical equivalence with a picture that will hopefully be worth 1,000 words, let's take 2 sentences and prove that they are logically equivalent using a truth table. Sentence number 1. Either it will not rain or it will not snow. If we put this into logical notation, we have -r or -s, which is read not r or not s. Sentence number 2. It will not both rain and snow. Put into logical notation, this would be dash, open parentheses, r and s, close parentheses, which is read not both r and s. So let's build a table to prove that our first sentence, not r or not s, is logically equivalent to our second sentence, not both r and s. Still, before we get to the truth table, we need to ask a question to determine if these two sentences are even candidates for the proof. And here's a question. Do they have the same sentence letters? Meaning, do they refer to the same basic information? Without much difficulty, we can answer in the affirmative because both sentences are talking about snow and rain. Furthermore, both sentences make observations about the weather at this exact moment. So are these two sentences logically equivalent, even though they appear to be completely different? Let's look at the truth table. Let's begin by setting it up. On the far left, we have our two most basic statements. They are R and S. Remember that to figure out the number of rows we are working with in a truth table, we must get the power of 2 that is equivalent to the number of statements we are trying to evaluate. In this case, we have two statements, R and S, so we get the second power, or 2 squared, which gives us a total of 4 possible outcomes. We fill in these first two columns with the appropriate possibilities of true and false, here denoted by T and F. And now we can begin to fill in the rest of our table. R and S. This is a conjunction because it has the ampersand between the two statements. And you will remember from part 1 that a conjunction is only true if all of its parts are true. That means if we combine R and S from the first two columns, there is only one possible value of the conjunction R and S that is true, and that is the one in the first row. The remaining 3 rows will be false. In the fourth column, however, we have the denial of our previous column. A denial means that we must supply the opposite truth value, so now our first row is false and all the rest are true. This fourth column is the expression of our second statement that we are evaluating for logical equivalence. It was, it will not both rain and snow. Now let's quickly fill in the rest of our table. For columns 5 and 6, we must supply the denied value for the R and S columns given earlier. Remember, a denied value is the opposite of the original. So where R is true, not R will be false. And where S is true, not S will be false. And that leaves us with our final column. This column represents our first sentence that we are evaluating. Either it will not rain or it will not snow. The denials of both R and S are disjoined by the or. Since a disjunction evaluates to true whenever at least one of its parts is true, we can fill in the rest of our table, and upon completing this step, we can compare both columns, not both R and S, and then the second column, not R or not S, and we see that although our two sentences were very different, they are in fact logical equivalents, because all of their truth tables are identical in all possible cases. Having demonstrated how the logical equivalence definition works, it's time to make an observation about parentheses in logic. We use parentheses to separate letters when part of a sentence refers to the combination as a whole. Let's look at our second sentence from our discussion of logical equivalence to see what happens if we do not include the parentheses. Our example sentence was, it will not both rain and snow. We used dash, open parentheses, R, ampersand, S, close parentheses, to demonstrate logical equivalence. But why didn't we use dash R, ampersand, S? Well, rain is represented with R, snow with S, the and, as a conjunction, is represented by the ampersand. That leaves us with R, ampersand, S, R and S, which is pretty simple to see. The not is also pretty obvious. It's represented by a dash. But what we're trying to figure out is the relationship of this dash to the rest of the sentence. And for the purposes of logic, it should be pointed out that whenever we see either combined with or both combined with and, we should assume that the two items are joined together. When we write out such sentences, we would replace both and either with the opening parentheses. That explains why we put it in parentheses, but what happens if we leave them out? Well, the next point on the slide demonstrates that we will very likely be misunderstood if we do leave out these parentheses. If we write not R and S, someone would most likely think that we are conjoining the denial of R and S, when what we are really trying to say is the denial of the conjunction of R and S. In summary, parentheses are vitally important to improve understanding when confusion is possible. And so, with these new basic principles in mind, and with our new definition of logical equivalence being proved, let's move on to our first law of logic that we are going to discuss in this video. And that is the law of double denial. The law of double denial states that any statement beginning with a pair of denials is logically equivalent to the sentence obtained by erasing the first pair of dashes. So a pair of denials is represented by a pair of dashes. And our first sentence for analysis is, "It will rain." We'll let that be R. If we deny this sentence once, we have "it will not rain," which would be dash R. But we're trying to figure out a double denial here. So let's add in yet another case of the word not into our sentence. This will leave us with our second proof sentence, which is, "It is not the case that it will not rain." And we're going to write this in logical notation as dash dash R. Now let's take this law to a truth table to prove that the law of double denial does in fact hold true. The statement R can only have two possibilities, true and false. The denial of R is the opposite of R's values, but we're going one step further, the double denial, not R, and we flip the column for not R one more time, arriving at T and F. So, as you can see, our first and third columns are in fact identical, and we have proved that the double denial of a statement is in fact logically equivalent to the original statement. Just one other note about the law of double denial. Logical equivalence can also be verified for a statement that is denied once, and then comparing it to a statement that is denied 3 times. So basically, dash 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 R is going to be logically equivalent to dash R, because if we removed 2 dashes, we would wind up with the same pattern. So that's it for the law of double denial. Let's move on to our next law, De Morgan's law, which has 2 forms, one for a conjunction and one for a disjunction. De Morgan's law can first be expressed: the denial of a conjunction is logically equivalent to the disjunction of the denials of the components. Now, if you look at the example underneath the expression of the law on the slide, you'll probably notice a similarity to our example that we used to verify logical equivalence at the beginning of this video. So if you want, you can scroll back in time on the slider bar down below and look at the table. We're not going to go back to it for right now. We've already proven that not both R and S is logically equivalent to not R or not S. So let's move on to the second version of this law. The denial of a disjunction is logically equivalent to the conjunction of the denials of the components. Really, the only difference is that we've changed the spot of the disjunction and the conjunction. So let's set this up as a truth table as well. Again, first 2 columns are pretty self-explanatory. We have 2 statements that we are analyzing, so we have 4 possible outcomes. We've alternated T and F on the first 2 columns so that we have all possibilities accounted for. The third column is a normal disjunction of R and S, meaning that we have 3 T values and 1 false value. Now, because we are denying the disjunction for the first part of our sentence that we are evaluating, we will need to reverse the values that we have in the third column, leaving us with the top 3 rows being false and the 4th row being true. Rows 5 and 6, pretty self-explanatory once again. We've just flipped the values of columns 1 and 2 because we are denying the original statement. You can see those being expressed down the columns, leaving us with the ability to figure out the truth value of the conjunction not R and not S. Again, a conjunction is only true if all parts of the conjunction are true, so our first 3 rows are false and the last one is true. And if you compare columns 4 and 7, you will see that indeed not both R or S and not R and not S are logical equivalents, and De Morgan's law is accurate. Let's move on to our third law for this video, the law of absorption. This law states that when some component of a disjunction differs by only the presence or absence of a dash from some component of the conjunction, we may drop the redundant component of the conjunction. That's a lot of words. Let's take some time to unpack it. First, we start with the disjunction, because we are talking about a component of a disjunction. in the definition. That's the very first thing that we see. So let's, again, use our two statements about the weather, R or S. But we can also deny the R and have not R or S. But then we need to go a step deeper because one element of the disjunction must be a conjunction. And even more specifically, it needs to be a conjunction with the same letter as the other part of the disjunction. But yet again, we need to get even more specific. The component of the conjunction must be the opposite truth value of the similar component in the disjunction. As we can see from the first example on the slide, if the value of the common letter is just a letter, then the value in the conjunction for the law of absorption to take effect must be the denied letter. Then the opposite will be true in example 2. So let's demonstrate that our two proof statements are correct using a truth table. Again, we have 4 possible outcomes because we are only analyzing 2 statements. We have a very simple disjunction set up in the third column, R or S, which is true in the first 3 possibilities and false in the last one. Column number 4, we have a conjunction, R and S, which is only true if all parts are true, so the first row is true and the remaining 3 are false. We have denied R in the 5th column. That leaves us with the opposite values of the first column. So then when we have a conjunction of not R and S, we will need to figure out how not R is related to S. Not R or not S, this is one of our proof statements. We must look at the column for not R, and we must combine that using a disjunction with the column for S. And again, because we're using a denial, it's going to look a little bit different than normal, but the rule is still the same. Anytime a disjunction has at least one part of its sentence that is true, the whole disjunction will be true. That leaves us with a total of 3 possible outcomes, the first, third, and fourth, with the second row of the table being the only one that can possibly be false. Now, in order to verify that our third column and our 8th column are in fact logically equivalent, we need to get the disjunction of R and not R and S. We've already figured out not R and S. That was in column 6, so let's get the disjunction of the values from columns 1 and column 6. And when we check that with column number 3, column number 8 is indeed logically equivalent. Again, for the last column in our table, column number 9, we have not R disjoined from the group both R and S. So if we get the disjunction values of not R and S, which is from columns 4 and 5, we will find that we have T, F, T, T, which matches with column number 7. Therefore, we can see by simply applying the normal rules for conjunction, disjunction, and denial that the law of absorption does indeed arrive at logically equivalent statements. Now let's move on to our last law for this video, the law of redundancy. This law is really much less complicated than the others we have been discussing, but proving it requires a little bit more work because we have to add a third statement to our truth table. We're now analyzing a combination of 3 statements. Here is our truth table. Again, we must get the cubed power of 2 because we are analyzing 3 statements. But as we're filling out the values, there is a very slight catch. R is always equal to R because its identity is R. We have to write the first 4 rows as true for R and then the second 4 rows as F. When we get to S, we write TT, FF, TT, FF. And normally, if this was in fact a different statement, we would write TF, 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 all the way down the table. But you can't do that this time because R is equivalent to the first R. So the first 4 rows, again, are T, 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 followed by F, 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 F. The conjunction R and S follows the same normal rules for conjunction. Now here's where it gets a little bit more complicated. We have 3 values now, right, in column number 5? But actually, the same rules apply. All you have to do is look across the table. That's why you create these tables, because when you add in more components, it becomes easier to just look, evaluate with the same rules for all the statements. You know immediately that because you're working with conjunctions, If a single one is false in the line, then the whole sentence will be false. R and S and R. If we analyze the first three columns together, in the first row and second row, all three values are T. So again, the first and second row in column number 5 will be T. But after that, in the first three columns, R, S, R, we have a false, at least one false. Therefore, column number 5 will end with 6 F values, meaning that R and S and R and S and R are actually logical equivalents. They match. When we move on to column number 6 with our disjunction and trying to prove that the disjunction of R and S is logically equivalent to the disjunction of R and S and R, now we're working with the other kind of logical notation that we learned last time, a disjunction, which will have true as its truth value if even one of its parts is true. R and S have at least one truth value in columns 1 and 2 from rows 1 through 6. Therefore, the first 6 rows of column number 6 will be true and the last 2 will be false. Now let's see if the disjunction of R and S and R is, in fact, logically equivalent to the disjunction of R and S. Again, don't despair because there are 3 statements that we are analyzing. They still use the same rules for disjunction as a sentence with 2 statements. R or S or R. If all parts of the sentence are true, if one part of the sentence is true, then the whole sentence is true. If all parts of the sentence are false, then the whole sentence is false. So let's look at our first row. R is true, S is true, R is true. Therefore, in R or S or R, our first row is true. Our second row also has true in all possible cases. Therefore, the second row in our 7th column is also true. Now, as we move down the row, we're doing the exact same thing as we've done all the other truth tables, checking the validity and seeing if there's at least one true statement. If there is, we report true in column number 7. If there's not, then it's false. After we have done that, we look down our table and we find that indeed R or S is logically equivalent to R or S or R. Repeating elements may indeed be dropped out of either a conjunction or a disjunction to yield a logically equivalent sentence. And with that, we have now arrived at the conclusion of part 2 in our series about logic for intercultural studies. Be sure to check back next week for the continuation of our study with part 3. In the meantime, why don't you consider checking out the Russian Word of the Day video series, where I release a short video every morning so you can build it into your daily routine. If you're not interested in studying Russian, though, I recognize not everybody is, please support the channel with a like, and don't forget to subscribe so you are alerted when future videos come out. Thanks so much for watching. We'll see you again soon, but until then, get curious and start digging.